The question feels almost childlike. If the universe is expanding, there must be something outside it, some vast emptiness it is pushing into. You picture it instinctively, a balloon swelling inside a room, everything rushing outward toward an edge. That image carries three hidden assumptions: that there is an outside, that there is an edge, and that empty space was already waiting to be filled. According to general relativity, all three are wrong. The universe may not be expanding into anything at all, and what that actually means is far stranger than the void you are imagining. The mind reaches for something familiar, a balloon swelling inside a room, its surface stretching outward, pressing against the air. In that picture, the universe is a thing with a shape, surrounded by an emptiness just waiting to be filled. But the balloon image smuggles in three quiet assumptions: that there is an outside, that there is an edge, and that empty space exists beyond, ready to receive whatever expands. Pause on each of these for a moment. An outside, somewhere the universe could move into, as if the cosmos were an object inside a larger container. An edge, a boundary where the universe stops and the outside begins, sharp as the skin of a balloon. And a waiting emptiness, a vast, silent void that exists on its own, indifferent to whether anything fills it. Each feels natural, almost automatic. Each is wrong. General relativity, the theory that underpins all of modern cosmology, does not describe the universe as a thing inside something else. There is no external space, no invisible room, no cosmic container, no edge lurking at the farthest galaxy. The expansion is not galaxies flying outward through emptiness, like shrapnel from an explosion. Instead, the distances between galaxies grow because the very fabric of space-time stretches everywhere at once. There is no center, no edge, and no outside to push into. The universe is not moving through space. Space itself is changing. This idea runs against every instinct. If there is no outside, what does it mean to expand? If there is no edge, where does the universe end? And if there is no pre-existing void, then what exactly is growing? The old picture collapses, but the replacement is stranger still. To make sense of it, a new kind of map is needed. A way to describe a universe that contains all of space, with no beyond and no boundary to cross. But that raises a worse problem. In 1922, Alexander Friedmann sat with Einstein's equations and found something no one expected. The mathematics allowed for a universe where space itself could stretch or contract. Not a static arena, but a living geometry governed by a single ingredient, the scale factor A of t. This number is not a distance, not a speed, but a silent multiplier. As it grows, every proper distance in the universe grows with it. Galaxies that stay motionless in their own patch of space, fixed in so-called moving coordinates, still see the gulf between them widen, not because they are moving, but because the ruler itself is changing. The Friedmann-Lemaitre Robertson-Walker metric, or FLRW, is the map for this reality. Its line element encodes a universe where every point is like every other, and expansion means the grid of space stretches everywhere at once. The scale factor A of t tells how much the universe has grown since a chosen starting point. If A of t doubles, every proper distance between moving galaxies doubles too. There is no edge, no boundary where the stretching stops. The universe is not swelling inside a larger void. It is all there is. The stretching is not a force pushing things outward, but a change in the metric that defines what distance means. Cosmologists keep two kinds of distance in mind. Proper distance is the actual separation between 2 points at a fixed moment in cosmic time. Moving distance is a coordinate label that stays constant for objects moving with the flow of expansion. As A of t increases, proper distances grow, but moving distances do not. Galaxies held in place by gravity, like the Milky Way and Andromeda, ignore this stretching locally. But on the larger scales, where nothing binds, the expansion of space itself carries galaxies apart, while each remains still relative to its own patch of the cosmic grid. Friedmann's equations, derived from general relativity, show how the scale factor evolves, shaped by the energy and matter in the universe. The result is a cosmos where the distances between the farthest galaxies increase, not through motion, but through the slow unfolding of space itself. If there is no outside and no edge, then what expands is not the universe into something else, but the very meaning of distance from within. Yet, if space stretches everywhere, how are we to picture this expansion at all? The old analogies begin to crack. The balloon analogy lingers in classrooms and textbooks, a favorite for its simplicity. Imagine galaxies as dots on the surface of a balloon. As the balloon inflates, the dots move farther apart, not because they travel across the surface, but because the surface itself stretches. No dot sits at the center. Every location sees every other recede, and there is no privileged vantage point. This is its strength. It banishes the idea of a cosmic center and hints at a universe where expansion is everywhere, not radiating from a single place. But the analogy carries a hidden flaw. The balloon floats in a room, surrounded by air, watched by an observer outside. In the real universe, there is no outside, no air, no higher dimensional space waiting to be filled. The surface of the balloon is two-dimensional, embedded in three, but our universe, as described by general relativity, is the entirety of space itself. There is no external arena, no cosmic laboratory where the universe grows larger inside something else. The moment you picture the balloon swelling into a room, the metaphor betrays you. The temptation is strong to ask, what is the universe expanding into? As if there must be a larger emptiness beyond. But every observation, every equation, points the other way. Space expands from within, not into. The distances between galaxies grow because the metric that defines space stretches everywhere at once. There is no edge to cross, no territory to invade. Some educators prefer the raisin bread model. As the dough rises, raisins move apart, but the bread itself is all there is. Or the expanding grid, where the lines themselves stretch, but nothing moves through a background. These pictures avoid the trap of an outside, yet even they are just metaphors, useful but incomplete. The universe's expansion is a change in the rules of distance itself, a transformation with no external frame. But if space can stretch so profoundly, what happens when the expansion itself goes wild? The next chapter in cosmic history answers with a speed beyond imagination. In the first split second after the beginning, the universe did not expand at a gentle pace. It erupted. The moment known as cosmic inflation arrived not with a bang, but with a silent, overwhelming surge. For a brief interval, less than a trillionth of a trillionth of a trillionth of a second, around 10 to the minus 32 seconds, the scale of the universe ballooned by at least a factor of 10 to the 26th power. If a single atom had grown this quickly, it would have become larger than the Milky Way in an instant. The idea of inflation came from the mind of Alan Guth in the early 1980s. He was searching for a way to explain why the universe looks so smooth and flat, why distant regions share the same temperature, and why no relics of exotic physics, like magnetic monopoles, have ever been found. The answer, Guth realized, was to let space itself stretch at an unimaginable rate, smoothing out any wrinkles, diluting any leftovers, and blowing away irregularities before the hot Big Bang even began. During this fleeting moment, the entire observable universe grew from a subatomic speck to something the size of a grapefruit or larger. The numbers are almost beyond comprehension. In less than 10 to the minus 32 seconds, every distance grew by a factor of at least 10 to the 26th power. The energy that drove this expansion, the so-called inflaton field, left behind faint quantum ripples, tiny fluctuations that would later seed galaxies and clusters. Inflation ended as quickly as it began, but the aftershocks shaped everything that followed. The cosmos emerged vast, smooth, and nearly flat, ready for the slower unfolding that would build stars and galaxies. The old question, what is the universe expanding into, becomes even stranger here. Inflation did not push into a waiting void. It created the very stage on which all cosmic history would play out. But if space can stretch by such an absurd amount, and in such a short time, what limits remain? What does it mean for the edge of the observable universe, or for the speed at which distant galaxies recede? In 1929, Edwin Hubble measured the faint glow of distant galaxies and uncovered a pattern that would reshape our understanding of the cosmos. The farther a galaxy lies from us, the faster it appears to recede, a relationship now known as Hubble's law. Written simply as V equals h0 times d, this law suggests a universe in constant motion. But the truth is more subtle, and always has been. The speeds in Hubble's law do not describe galaxies racing through space. Instead, they measure how the space between us and those galaxies stretches. For nearby galaxies, this stretching is gentle, just tens or hundreds of kilometers per second. Yet as distance increases, so does the calculated speed. At a certain threshold, Galaxies with redshifts above about 1.5 are receding from us faster than light. Today, this boundary sits at roughly 4.3 billion light-years, marking the Hubble radius. Beyond it, galaxies are carried away at superluminal speeds. Einstein's special relativity sets a speed limit for objects moving through space, but not for the expansion of space itself. No galaxy overtakes a photon in its own neighborhood. The universe's expansion is not a force pushing galaxies outward, but a change in the metric, the very ruler of space. Galaxies beyond the Hubble radius are not off-limits. Their light can still reach us if the expansion slows or the Hubble radius grows. We see galaxies at redshifts of 2, 3, or higher, their light beginning its journey when they were already receding faster than light. This has always been the case, from the earliest times to now. The farther we look, the faster the gulf grows, not from motion, but from the shifting meaning of distance. This raises a new question. Are there places forever beyond our reach? And where does the observable universe truly end? There are boundaries in the universe, but they are not walls or edges. They are horizons, limits set not by matter, but by the speed of light and the story of expansion itself. The first is the particle horizon, the farthest distance from which light has had time to reach us since the beginning. Its radius is about 45 or 46 billion light-years. This number is not the age of the universe in years multiplied by the speed of light. Space has stretched along the way, so the photons we catch today began their journey much closer, crossing a gulf that grew beneath them. Even farther, there is a second, subtler boundary, the event horizon. This is not about what we see now, but about what we could ever see, even if we waited forever. The universe's expansion, driven by dark energy, means that some regions are slipping away so quickly that their light, sent now or in the future, will never reach us. The event horizon sits closer, about 16 or 17 billion light-years out. Anything beyond it is forever cut off, no matter how patient we become. These horizons are not objects, they are consequences of the rules that govern space and time. The observable universe is not the whole universe. It is the sphere carved out by these limits, the region from which signals have had time to arrive, and the patch of sky whose future stories we are allowed to witness. What lies beyond remains silent, not because it is hidden behind a barrier, but because the rules of expansion draw an invisible line. The universe, it seems, is both larger and more unreachable than any simple analogy can contain. In the late 1990s, two teams set out to measure the fate of the universe, expecting to find signs of gravity slowing the cosmic expansion. The High-Z Supernova Search Team, led by Brian Schmidt and Nicholas Suntsev, and the Supernova Cosmology Project, headed by Saul Perlmutter, gathered data from distant Type Ia supernovae, stellar explosions so reliably bright that they serve as cosmic mileposts. By comparing how faint these supernovae appeared to how far away they ought to be, the teams could chart the universe's expansion history. But as the data accumulated, a pattern emerged that defied every expectation. The most distant supernovae were dimmer than predicted, not because they were farther away in a slowing universe, but because the expansion itself was speeding up. The Hubble diagram, the plot of supernova brightness against redshift, refused to fit any model in which matter and gravity alone shaped the cosmos. Only an added ingredient, something with a repulsive effect on large scales, could explain what the team saw. Cautious and meticulous, both groups checked for every possible error, interstellar dust, calibration mistakes, hidden biases in their sample. Yet the results held. In 1998, both collaborations announced that the universe's expansion is accelerating, a finding so unexpected that it sent shockwaves through physics. The discovery earned Perlmutter, Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. The headline spoke of a new cosmic force, dark energy, whose nature remains unknown. The universe, it seemed, was not just expanding, but racing away from itself, driven by something no one had anticipated. The story of cosmic acceleration settles into uneasy territory. For over 2 decades, astronomers have tracked the universe's expansion with ever-increasing precision, searching for hints about the nature of the force behind it. The simplest explanation is a cosmological constant, an unchanging energy woven into the fabric of space itself, with an equation of state parameter, W, exactly equal to -1. This idea fits the data so well that it has become the backbone of modern cosmology. Yet the question remains, is dark energy truly constant, or could it evolve over time, rewriting the fate of everything? The dark energy spectroscopic instrument, called DESI, now maps millions of galaxies and quasars, building a three-dimensional atlas of the cosmos. With its first-year results, DESI found W hovering at precisely -1, with a margin of error so slim, just a few percent, that any sign of change would stand out sharply. But as the collaboration extended its reach to higher redshifts, subtle patterns began to appear. In the regime where dark energy should be weakest, above redshift 1, a slight drift in W surfaced, a tilt, not a leap, and still compatible with a cosmological constant within the uncertainties. DESI spokesperson, Dr. Rongguo Zhang, cautions that these are only hints, provisional and subject to revision as more data arrive. Internal debates swirl around the possibility of systematic errors, the limits of redshift space modeling, and the relentless push for independent confirmation. For now, the best fit numbers remain stubbornly close to -1, but the provisional DESI results leave the door ajar. If dark energy evolves, even slightly, the future timeline of the universe could change in ways both subtle and profound. The fate of distant galaxies and our own cosmic isolation hangs on the answer to a question that is still unresolved. 100 billion years from now, the universe will be almost unrecognizable. The Milky Way and Andromeda, long since merged, will drift through a darkness that grows deeper with each passing epoch. Distant galaxies, once scattered across the night sky, will have slipped beyond the cosmic event horizon. Their light, stretched by the accelerating expansion, will never reach us again. To future astronomers, the universe will appear empty, with only the faint remnants of the local group, surrounded by silence. The timeline unfolds with a slow, relentless certainty. Star formation, already in decline, will grind to a halt somewhere between 1 and 100 trillion years from now. The last stars will flicker out, leaving behind white dwarfs, neutron stars, and black holes. With no new light born, the sky will fade to black, illuminated only by the afterglow of long-dead suns. What happens next depends on the true nature of dark energy. If the expansion is driven by a cosmological constant, if W remains at -1, the universe approaches heat death. Temperature falls toward absolute zero, and all gradients vanish. But if dark energy is more exotic, with W dipping below -1, a different fate looms: the Big Rip. In that scenario, the scale factor surges to infinity in a finite time, tearing apart galaxies, stars, even atoms themselves. For now, observations keep the future balanced on a knife edge, with the numbers holding close to -1, but the possibility of a more violent end always lingers at the edge of calculation. In every scenario, isolation deepens. The universe's expansion does not carry us into a wider emptiness. It stretches the very fabric of reality, drawing every distant possibility beyond reach. The long night ahead is not a journey outward, but a slow erasure of connection, written into the mathematics of space and time. Tonight, the galaxies do not drift through space. They are carried apart as space itself expands, with no outside at all. The universe's acceleration, measured by the dark energy spectroscopic instrument and other surveys, means every distant light will one day fade from view. What then are we truly inside of? The answer is stranger than emptiness, a cosmos with no beyond, only the growing silence between. Share your thoughts below.